Hi everybody. Welcome to this video on practice problems relating to stoichiometry. So today we're going to talk about 4 different problems with 4 different ways to ask questions about stoichiometry and those types of problems. These problems will directly apply to your chemistry classes for say in high school or for in college or any general chemistry. For this first problem, in the following reaction, if 10.4 grams of zinc reacts with 15 grams of copper 2 chloride, what mass of zinc 2 chloride can be produced? So here we have our chemical reaction below, or this is our recipe, where an atom of zinc is reacting with a molecule of copper chloride, or CuCl2, and producing zinc chloride and copper, where we have 10.4 grams of zinc, and then we also have 15.0 grams of copper 2 chloride. Now, each of these, if you've seen the previous shorts or the previous videos, stoichiometry relates the amount of substance by counting, and mass or grams is not a unit of counting that we can use to relate. With this recipe above, the first thing we should have done, and the first thing we will do, is to make sure it's balanced on both sides, or we have a balanced chemical reaction, where our elements are balanced on both sides of a reaction arrow. So if we count zincs, we have 1 zinc on both sides, so zincs are good. If we look at copper, we have 1 copper on the left side and 1 on the right side, so we're good there. If we look at chlorine, we have 2 chlorines on the left side and 2 on the right side, so we're good there. So we know our reaction is fully balanced. Now, with this, all of these have a 1 in front of these, so we can actually get different conversion factors. Or we can say 1 mole of zinc makes 1 mole of zinc 2 chloride. And the same thing with our copper 2 chloride. Makes 1 mole of zinc 2 chloride. This is just the conversion factor we can get from this recipe. And we'll use that here in a moment because we're trying to find the mass of zinc 2 chloride in the end. Now, when we do these stoichiometry problems where we're given the grams of a reactant and we're trying to find the grams of a product, we have to take this specific roadmap. Let's say we have mass of a reactant. We have to go to the moles of a reactant using molar mass, which I'm just going to give you as a big M. And then with this roadmap, we're going to go to moles of a reactant. And with our recipe, we can go to moles of our product. And this is using the conversion factors we found above. And then with our moles of our product, we can go to our mass of our product using another molar mass relating to our product. So this is the roadmap that we're going to take. I moved the below here for just room for our calculation. But now we have our grams of our zinc and we have our grams of our copper 2 chloride, which are our reactants. Let's see how much product they can actually make. So with our grams of our zinc, if we use our table, we want to go from grams to zinc to moles of zinc. So we have to use the molar mass that we would find on the periodic table, which is 65.38 grams per mole. And we'll put that here on the bottom. Grams of zinc for every mole of zinc. The reason why I put the molar mass on the bottom in our table is because of how the units will cancel out, where our grams of zinc will cancel out, and now we're left with moles of zinc. So that's why you put your molar mass in the bottom of this table. Now, using our conversion factor above, we can say 1 mole of zinc is equal to 1 mole of zinc chloride. And then using the molar mass of zinc 2 chloride, we can convert from moles to grams. And the molar mass of zinc 2 chloride is 136.29 of zinc chloride for every 1 mole of zinc chloride. So this is the full table that we'll need, and all our units will cancel out nicely to give us the mass of zinc 2 chloride. And when you end up doing this full calculation, we'll round to around 3 sig figs. We can produce 21.7 grams of zinc 2 chloride. Now let's do the same thing with the copper 2 chloride below. Let's do the same procedure, just with different molar masses and the same but different conversion factor. So here, copper 2 chloride has a molar mass of 134.45 grams per mole of copper 2 chloride. And then we use our mole to mole ratio, where 1 mole of copper 2 chloride is equal to 1 mole of zinc 2 chloride. And then we're going to use our molar mass of zinc 2 chloride, as we did before, for every mole of zinc 2 chloride. And what we'll get is a mass of around 15.2 grams of zinc 2 chloride. These masses that we found are the amounts the individual reactants can possibly make. This is the idea of finding out about how much you can actually make theoretically, is the idea that copper 2 chloride can only make 15.2 grams of zinc 2 chloride before copper 2 is completely gone, or copper 2 chloride is completely gone. So copper 2 chloride is the limiting reagent, which means the amount that it makes is the amount of mass that can be produced. So this means a maximum of 15.2 grams of zinc 2 chloride can be produced in this specific reaction with this amount of material. And that is because copper 2 chloride will be completely gone. So this is a very basic stoichiometry problem. You're given grams of your reactant, and you're trying to find the grams of your product, while you're given two different reactants with two different amounts. You're given the grams of your reactants, and you're trying to find out about how much product can actually be made. Let's move on to a second problem. Here, if 104 milligrams of substance A2 reacts with 157 milligrams of substance B2 to produce AB, what is the theoretical yield of substance AB in milligrams? Theoretical yield is another way of saying the grams that can be actually produced of substance AB, just like in the previous problem. Here, we're not given a recipe, but we're told about what this chemical reaction should look like. And so we should actually write our own balanced chemical equation before we do anything else. And if we read the problem over again, we said substance A2 will react with substance B2 to produce substance AB. So here is our chemical equation, but now we need to see if it's balanced on both sides. So if we look at substance A and substance B, relating to elements, here on the left side of the arrow, we have two A's, and on the right side we only have one. And the same thing for B. So the way to actually fix this is if we put a 2 in front of this AB, we'll end up changing both A and B, and we'll make it completely balanced. So now we have our balanced chemical equation. Using this, we can get those molar ratios again, where we say 1 mole of A2 is equal to 2 moles of AB. And the same thing for B2. Now, since we have those molar ratios, it's the same process as the previous page. But now we have milligrams, so we can convert them to grams. So we can convert them to grams using the conversion factor from grams to milligrams. If we have 104 milligrams of substance A2, using molar mass, we need to put it in grams. So we need to convert from 1,000 milligrams to 1 gram of A2. And now we use the molar mass that's given to you within the table of 13.0 grams of A2 is equal to 1 mole of A2. And now we use our mole-to-mole ratio as before, where 1 mole of A2 is equivalent to 2 moles of AB. And we can use our molar mass in the end of AB, which is given to you in the problem, 16.8 grams for every mole of AB. Now, the reason why I'm writing out all these units with their descriptors, such as milligrams of A2, grams of A2, and versus grams of AB, is because those are completely different. If you have milligrams on the left side of the table, it might not be the same thing as milligrams on the right side of the table. But milligrams of A2 does not equal milligrams of AB. So you have to keep that in mind. So we need to cancel out all the units that don't matter. Milligrams of A2 will cancel out. Grams of A2 will cancel out. Moles and moles. And you're left with grams of AB, which is what we want. And if you calculate this out, you can see that the amount of A2 given can produce a maximum of 0.268 grams of AB. And now let's do the same thing for B2. Here we have 157 milligrams of B2, and we'll go through the same process again of converting from 100 milligrams of B2 to 1 gram of B2. And then using the molar mass as before, 20.5 grams for every mole of B2. And then we use our mole-to-mole ratio that we have seen and we derived from above from the chemical equation, We have 1 mole of B2, making 2 moles of AB, and using the last molar mass of 16.8 grams of AB for every mole of AB. All the units cancel out nicely to what we need, where we're only left with the units of grams of AB. And when you calculate it out, the maximum amount that B2 can make is around 0.257 grams of AB. And like before, what this means is that the amount that these things can possibly make, once that amount of product is made, the respective reactant will be completely gone. So here, B2 will be completely gone after 0.257 grams of AB is made. So the idea is to find the least possible amount that can be made, which is 0.257 grams of AB, and that is the theoretical yield from all of your reactants, and comparing them all. So the theoretical yield of AB in milligrams, which we didn't do the last step, if you read over the problem one more time, we need the answer to be in milligrams, and if we use the conversion factor of grams to milligrams, again, 0.257 grams of AB, if we just use our table one last time, 1 gram of AB is equal to 1,000 milligrams of AB, leaving you with 257 milligrams of AB as your final answer. And that's it. Now, let's move to a little bit more of a difficult problem with the idea of figuring out how much reactant is actually left over, not just by figuring out how much product is made. So for here, a chemist synthesizes calcium hydroxide in the following reaction. If 1 kilogram of water reacts with 50 grams of calcium oxide, how much water theoretically remains after the reaction is completed? Here is our chemical equation. We need to make sure it's balanced already. We have 2 hydrogens on both sides, we have 1 calcium on both sides, and we have 2 oxygens on both sides, so it is balanced. So we have the 1-to-1-to-1 relationship of every single reactant and product, which is good. Now, it doesn't say to find how much product to make specifically, but it's very good to figure out how much product can actually be made to compare to see what is your eliminating reactant, or which one will run out first. So if you look at the amount of water that we have 1 kilogram of water, which is a large amount of water. So my intuition is telling me that water is most likely not going to be the limiting reactant. But let's prove that below. So here we have 1 kilogram of H2O. If we convert it by using 1 kilogram of H2O to 1,000 grams of H2O, we need to convert from grams to moles, and the molar mass that you would find on the periodic table of 2 hydrogens and 1 oxygen is 18.02 grams of H2O for every mole of H2O. And using our mole-to-mole ratio of 1-to-1, 1 mole of H2O to every 1 mole of calcium hydroxide, we can stop there. We don't need to figure out how many grams of calcium hydroxide that need to be made, because we don't really care about that. The moles of calcium hydroxide made from one reactant to another reactant can be compared in the mole form and not just the gram form. And so if you calculate this out, and for sake of this problem, we're going to add an extra 0, just in case if you're worried about sig figs in this specific problem, and we'll end up getting a theoretical yield from just our water of 55.5 moles of calcium hydroxide. Now let's do the same thing for our calcium oxide. Here we have 50 grams of calcium oxide, and if we use our molar mass of calcium oxide, where we have 1 calcium and 1 oxide, with a molar mass of 56.08 approximately grams per every mole of CaO. And then we use our 1-to-1 mole ratio again. So this table is actually pretty short of calcium hydroxide and calcium oxide. All the units will cancel out and we'll be left with moles of calcium hydroxide, which is good. We'll be left with an answer of 0.892 moles of calcium hydroxide. This means only 0.892 moles of calcium hydroxide can actually be made, because once that is made, all your calcium oxide is gone. So we know our limiting reagent is calcium oxide. So after this reaction is completed, calcium oxide will run out. But the interesting thing is, there's going to be some water that is going to be used up in this reaction as well. And there'll be some water left over as a result, because it's not our limiting reactant. So we can actually use a mole-to-mole comparison of water and calcium oxide, even though they're both reactants, because this is a recipe that we're actually using. So if we use our 50 grams of calcium oxide, convert it to moles, as usual. For every mole of calcium oxide, 56.08 grams. And now we actually have a 1 mole of calcium oxide to 1 mole of water, which is actually really cool. The 1-to-1 mole ratio from our reactants can actually retain as well, not just react in the product. And we can take this one step further and convert this to mass by using the molar mass of H2O to make our lives easier here in a second. Now, this calculation will actually tell us the amount of mass that is used up within this reaction, because the amount of calcium hydroxide that will actually be used up, which is 50 grams, will use up this much water as well. And if you calculate it out, you'll get 16.1 grams of H2O will be consumed, because this is the amount of water that is needed to react with 50 grams of calcium oxide, which means we need to figure out how much water theoretically remains after the reaction completes, right? If we start with 1,000 grams of water, or 1 kilogram, if we subtract, ignoring any sort of sig fig problems here, if we subtract 16.1 grams of water from that, we can see that there is actually going to be 983.9-ish grams of water remaining. So the final answer is actually 983.9 grams of H2O. It doesn't say to convert it back to kilograms, but this would be the answer in grams. So that's another way they can actually ask you the problem, is to figure out how much of your reactant actually remains. In the first problem in the video, a calculated yield of 15.2 grams was found. If the reaction only actually produced 12.4 grams in the experiment, what is the percent yield? So this is the idea of finding your percent yield within your reaction to see how much or how ideal your reaction is. So here, the theoretical yield is 15.2 grams, and your actual yield is 12.4. Your actual yield will always be smaller than your theoretical yield. You'll never actually approach 100%. But to find your percent yield, all you'll have to do is take your actual yield and divide it by your theoretical yield, and then multiply it by 100 for a percentage, and you'll actually end up calculating it here. So 12.4 grams divided by 15.2 grams times 100 will result in an 81.6% yield, which is actually pretty good for a typical reaction. But this is the idea of how percent yield can also play a role in your problems. So it could actually be a two-step problem where you find your theoretical yield from your calculations, then your actual yield will be given to you because it will be from an experiment that will be conducted or simulated. I hope you have learned something today. Please comment any questions you may have for me about stoichiometry or about any troubles you have understanding this video. Please like this video and please subscribe to my channel for more chemistry and math related problems.